Welcome back. And off we go for the right side of this question. We're supposed to draw ACOH. That's an oldie. An acetyl group, a Lewis structure. Oh my goodness, we got to show all the bonds and all the lone pairs. Well, give it some color. Acetyl is CH3 attached to carbonyl. Keep that in mind when we get to our biochemistry segment coming up after the test. Rest of the semester is biochemistry. Acetyls are everywhere in biochemistry. So there's the acetyl, the AC part. OH makes it an acetic acid. And it has a pKa of 5. And it becomes, oh, that's the product down here. We're using the conjugate base to take the proton off of either a secondary ammonium ion or a tertiary ammonium ion. Which one's going to be more reactive? Isn't that like flipping the question, which one of these is less stable? Isn't that the same question? Well, I'm going to tell you this is more stable because it's got hydrogen bonding twice and carbons twice for hyperconjugation. That's the most stable ammonium ion of the alkyl variety. And this one has a good amount of hyperconjugation, but limited hydrogen bonding. So less stable, it's going to react first. And it has a pKa of 10. Both the amines, I don't want you changing the number you memorized for an ammonium ion. Both of them have pKa's of 10. So 2 questions in a row, we're going to have an ammonium ion with a pKa of 10. This one I want you to take off the tertiary one. Before the secondary one. And 10 goes to 5, pKeq equals 10 minus 5. Reactant acid 10, product acid ACOH5. So this equilibrium is not favoring the direction shown, is it? That's not pKa. What happened? pKeq. And gotta have a nice small circle for the backwards arrow. Reactants are favored here. Now, oh, I forgot my formal charge on my ammonium on the bottom. I would have lost a half point. So we have an ammonium ion. It's going to take its H off. The base will take the ammonium's ions H off and become ethanol. I'll take 17 or 18 like you memorized for the other alcohols, but as an instructor, I like to remind you the 2 simplest alcohols, methanol and ethanol, both are really closer to 16. And we have an acid with a pKa of 10. Yeah, it's the conjugate base from the first reaction, but it's also the conjugate, it's the acid here that's going to react in the second reaction. It's just a little less acidic this time than the first time, not much. And I want the diamine down there. HN, CH2, CH2N, methyl, CH2, CH2N. There you go. And we're going to do a pKeq question down here. This one's a favorable direction. 10 minus 16 equals negative 6. 10 to the positive 6. Definitely going towards 16 away from 10. And the other one, we're going away from 10 towards 10 and sorry, that was not an acid. This is the acid. See, I'm confusing myself. This was the acid created. This was the acid reacted. We go away from the stronger acid back towards the weaker. And we have the answer to that one. And is there anything else on this page? No, it's a pretty full page. And moving on. Since we're on the acid-base theme here, remember yours will be just a little shorter than this. I think you're doing 7 molecules instead of 9. You'll definitely be comparing some alkylamines. Started right off here. I'm going to draw the conjugate acids here because sometimes we need to talk about the stability of those. And it's good review. At 2 NH2 plus for 1. At NH3 plus for 2. Phenyl NH3 plus here. And paranitrophenyl. Just draw it out. Paranitrophenyl NH3 plus here. So far, these are the worst bases. We lost a lot of resonance with the benzene. And we have 2 pyridine species. Pyridine's like an intermediate base. Not quite as good as imidazole, but better than aniline. Anilines, pyridines, imidazole. Oh, this one's called an oxazole. We'll talk about that when we get over there. And oh yeah, this pyridine's got some help. What do I mean with this one? Having help. Well, we have something that stabilizes carbocations up there, that methyl. So this cation's more stable than the one adjacent to it. So the base making this into this. If this is more stable, it means, well, we'll talk about it when we get there. I don't want to lose track of what I'm doing here. Where do we park the hydrogen as I'm copying the molecule? You'll tell me, well, in your mind, to put it on the sp2 nitrogen right there. Put it on the sp2 phosphorus so they can resonate here. Don't use that lone pair on the nitrogen. It's being used for aromaticity. Then we're going to use the old periodic trends in acidity after that. I hope you can see that, or remember that oxygen, not as big a resonator as nitrogen. It's more stingy with its electrons because of its high electronegativity. So I'm not liking this N plus as well as either of these two, N plus and P plus. Just thinking ahead. We don't have any guanidines here, although I'm just going to put a hint up here. I don't need to, but guanidine will show up here. Will show up here. And it will be your strongest base. Unless I have something even stronger, right? Like methyl O minus is stronger. It's got a negative pKb. We'll see. Where are we going here? We got the alkyls as the best that we have available here, the first two. And let's let's just say the best one is the secondary one. This is most stable, which means it's easiest to form. Most stable of these two, so easier to form. So 2 is not as basic as 1, and I put those in a box. Let's do some local comparisons and then put them all together at the end. How's that? Next 2 we should compare. This is more stable. Whoa, less stable over here. Less stable because NO2 pulls electrons away from N+, both by induction and resonance, N+. So, hey, you got something that's plus and you're trying to pull electrons away from it. Is that a good thing? Think about it. Cations are unstable. They're missing electrons, and you're trying to make it miss electrons more. That's not good. So in this pair, it's going to be a lot harder to make this one than this one. So I like 3 a lot better than 4. Some colors for circles going here. Actually, make the circles include the original molecules, huh? All part of the same discussion. And then we have 2 versions of pyridine. And hey, flip that argument backwards here. Instead of hurting like nitro does, methyl helps. So more stable because methyl helps with plus charge. And I need to see the word hyperconjugation. I should have seen some explanation here too. We had induction plus resonance. Electrons like going towards nitrogen in the nitro group, not away from. Okay, and we'll go over here. We say more stable, N+ with CH3 hyperconjugation. So that gives me this pair. It's green. I don't want green. I thought I had blue. Gives me this pair. Puts them in order. And that would make it easier to make this. So 6 is better than 5. Six is better than 5. 6 better than 5. Okay, these are all in the same family. I need to comment about the O not resonating as well. O doesn't resonate as well as N. Resonate as well. It's more of a hog with its electrons. Doesn't resonate as well as N. So IX weakest here. Oh, by the way, these are all imidazole variants. So they're going to be a little less basic, but better than these and worse than those 2. So these are going to be in the middle. What about P+ versus N+? When it was an anion, size was a factor. The size of factor with cations? Not so much. We're not trying to get a plus away from a plus. See, size helps electrons get away from each other. N plus is pulling those electrons closer to the nucleus than P plus, based electronegativity. So N plus closer to nucleus which is not a good thing. Electro negativity. So we can put these all in order now. IX is the worst of the bunch in these three. I want the P plus at the end. It's the best of the three. And I need VII in the middle. So right now we've got most of the credit already. We're almost all the way there. And the two alkyls at the end. The imidazoles right before that. We will have to add some comments. And the pyridines right before that. V and VI. And the anilines before that. And that was 4 before 3. We got 4 before 3. We got 5 before 6. We've got IX before VII, and we have 2 before 1. And some explanations underneath. Aliphatic better with better N plus with sp3 atoms attached. And these are all sp2 atoms with the plus charge, except for these guys, but they're attached to an sp2. So that does fit the argument. And these are sp2s. And the imidazoles, I should say extensive resonance helps them out. That's why they're second best. And the pyridines, sp2, but they do resonate. Write that down. sp2, but they do have some resonance. They get the normal benzene resonance, right? That helps. These resonate to other aromatics where the plus moves to a different atom. Here, I don't know, just got the other benzene resonance form. That's it. No big advantage there. These, you lose resonance when the nitrogen lone pair, lose resonance with the aromatic ring. There you go. So good answer, I think. There's a lot going on. We like our bases, and we're at a good stopping point, I think. I didn't check to see if there's something underneath. Yeah, retro is a good start for our next segment. And we're moving back here. Nothing at the bottom of that page. Yeah, and I'll see you very shortly after we get back from a break.